So yeah, all right. So let's see, who's new here? How many people took any CS class before this one? Hands up. Hands up. So the rest of you, oh, you did. CS classes, I mean in graduate school, not in college. Yeah. This is an introductory class. It has no prerequisites. We assume if somebody comes to the master program, they should be able to take this class. Easy, right? How hard can it be? Right? It doesn't have any prerequisites, like no algorithms, no data mining, no machine learning, no nothing, right? Should be easy, right? There's two problems with being easy. One is that it feels so easy. After today's lecture, everybody's gonna feel extremely happy. Everybody's gonna be like, wow, this is gonna be a piece of cake, right? Yeah, so that's the first problem, that you're gonna feel like that, and I have to work very hard to undo that feeling, you know, to get everybody on track. That's problem number one. Problem number two is it's double speed. Anybody took a class double speed before? Yeah? How did you feel?
Fast.
Yeah. So that's a problem. This is not for filming. This is for me to know the time. That's going to be a problem for this class more than for other classes, the double speed part. Because in theory, it sounds very good, right? Double speed, like instead of taking 2 classes, you take 1 class and you work twice as hard for that class, right? Yeah, but see, there's not double number of weekends. The weekends don't double up, and the time to eat and sleep, you know, doesn't work that way. So in practice, this is gonna feel quite rushed up. But our mandate is to do what we normally do in a regular class. So we'll try to do our best to do what we normally do in a regular class. Okay? So first things first, let's bookmark this page. I can write down the, see, that's a good chalkboard. A lot of chalkboard with the projector. So what do we have there? Some ccs.nu.edu /home/VIP. That's me, in case you didn't figure it out. Each I have course small c HTML index. That's where things are going to happen. So you need to bookmark this page. So that's kind of the intro, blah, 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 blah. There's a bunch of administrative issues, things like how to submit your homework. I'm sure people figure out quite easily. Some people took classes with me, it's the same system. We have a Dropbox folder. You're gonna set up your own Dropbox. You can use the one you have. If you don't have one, it's free to set up a folder. And you have to share that CS6200, your name, your last name, with a certain address that should be listed here. This address, this is username that the TAs and me will see your homeworks in it. Okay? Other things, we have a Piazza forum. I think mostly everybody by now is familiar with Piazza. So there's a link here with the Piazza forum where discussion is going to happen. Most questions about the homeworks and the content, I would like you to start with Piazza. Even though, I mean, there's no issues here with what if I ask a question and it feels stupid, what's gonna happen? There's no such thing, you can ask anything. What if I ask a question and I give away a big hint for the homework so the other students have it easy? No worries, no problem with that, right? So Start with Piazza, you can email directly me or TAs with personal issues, like, you know, I have a problem, or I want to know how I'm doing, or things like that. I'm going to be late. What else do we have here? So there is about the course. There is me and 4 TAs who would have office hours every day. Okay? So the main interaction between you and us, it's not in the lecture. In the lecture, it's me telling a story. The main thing will happen at office hours. There'll be 3 hours a day, office hours. They will have different rooms for different days. And we may have to adjust this depending on your schedule, if you have other classes, other commitments, so on and so forth. But is it at office hours that you essentially show your work, those assignments? If they're good, if the TAs checks them out, you get the points for that assignment. If they're not, you will be told what it is that's missing or what you have to fix, and then you'll come back. This is like customer support. It's like back and forth until you get it done. The good news is that almost everyone in this class will get an A because of the customer support, right? Even if you're not a good student, I hope everybody is, but even if you're not, if you try hard enough, you're gonna get an A. The bad news is it's gonna feel much harder than it looks. So again, you're gonna feel very good today, but once you hit homework 1 and 2, reality will kick in. Okay? So make sure you use a lot these office hours. The TAs will be there and they'll try to be ahead of you with all the homeworks so that they can answer your questions. This is an extremely hands-on class, as in the lectures don't matter much. This is just a story. What really matters is for you to get things done, which are those 8 assignments that we have during the term. So if we have, how many weeks we have? 14 weeks a full term, double speed is 7 weeks, and we have 8 assignments. So how many days per assignment is that? It's 6 days, maybe, without breakdown, not including weekends, right? So we're gonna look in a moment at homework 1, you kind of have 6 days to do it, okay? And then homework 2 kicks in. I'm not picky on the deadlines, but the DAs will be picky if you are late and we already moved to homework 2, and 6 days later we move to homework 3, and 6 days to homework 4, and still at homework 2 or homework 1. That's going to be impossible for TAs to handle that sort of load. Okay? So we're going to have to keep up a schedule as opposed to algorithms where we were like 3 homeworks behind. Again, I'm not picky on the homeworks in terms of the deadlines, but I think this needs to happen in time for everybody to keep up. There are 2 books that are not mandatory. All the information you need will be posted. In fact, one of them is online anyway. All the information will be posted and given to you, but they're there for reference. The Great Links doesn't work yet, but it will work. The Piazza Data Resources, you need a password for this. I'm not sure what it is. I think it's retrieval information. I think the DAs know about that. So you will need a password to access that data resources, like here's a data set, index this data, how do you get it? You get it from there. And then we have a schedule. Let me try to make this a little bigger. Which is organized on weeks, although because it's double speed, you're gonna see 2 weeks having the same dates on them. Because this is the weeks on the regular term, which means a double speed, we have to do 2 weeks per physical week, right? There's no class on Wednesday because it's a holiday. That's an additional issue for homework 1. So homework 1 will not be 6 days, it will be 9 days instead. So we catch another lecture on next Monday. If we need to, we'll come up with a makeup lecture, but I don't think we need to. So quickly, before I start the introduction, what is the content of the class? The first module you see here is retrieval models. That is, if I have an index and data, how do I basically search it? Basically, I mean, it's really basic search. That's not to be confused with what Google does, for example, when you type a query. It's the basic version of the search. That's module 1. In module 1, we're not going to create your own index. You're going to use a commercial indexing platform. Some of you may have used it already, Elasticsearch. How many people have seen Elasticsearch before? Hands up, okay. So it's easy to use. It takes a little bit of learning, but it's an extremely useful tool, even beyond this class. When you get outside an industry, you get a job, or you try to do something, having that skill, Elasticsearch, is a big checkup. So even though it takes some time to get it running, it will be very useful. That's for module 1. Now in module 2, when we talk about indexing, we're kind of going to repeat module 1, but we're going to do our own in-house indexing. We're not going to use Elasticsearch. Our purpose is to replicate the indexing and then run all the retrieval models just from homework 1. So that part will stay the same, except we're going to do our own indexing. Indexing has to do with how do we manage certain data objects, primarily text. There's of course indexing for images and songs and other things, but primarily for text. I'm going to ask a question in a few minutes. I'm going to say, why not use a database, for example, or some file, like a regular matrix or something. So you can think from now that I'm going to ask that question very soon. Why do we need indexing and not use something? Database has been around for what, 40, 50 years, a long time. So why databases are not good for indexing? Why we need a different mechanism for text, right? So once we have retrieval models, that's a way to search in an index once we have the data indexed. Indexing, it's a way to organize the data ready for search. And then crawling is a way to get the data to start with from the web. This might feel like a little bit like, why you start in the middle? Like, why don't we start with crawling, right? If we're to draw a pipeline here, like how the stuff actually happens. There is a data source, right? Let's say could be the web, or could be maybe medical records in a hospital, right? Or could be insurance documents. There is some data source. That's not our job. We assume that data's already, somebody else has the problem. Somebody else calls us and hires us to build their data. We're not data creators. So what happens next? We have a data organization, let's say indexing. Data. And then we have users with queries. Right? So now that we have organized the data, people want to find out things about it, like a web query. If you just open up Google and type a query, or maybe if you are a lawyer, you have a particular query, or if you're a doctor, you have a particular query. Doctors don't just go to the internet to find out answers, right? They may need to have a different data, differently organized than the web. So from those two, right, we get retrieval results. That includes a scoring mechanism or function. Okay, a mechanism or algorithm. Right? In other words, if I have an index and somebody asks a query, I need some sort of algorithm or mechanism or program to produce the answer. And finally, if somebody, never been in this classroom before, so I have retrieval results, Then I wanna measure quality. So evaluation, quality. Now, like in any data science, to get quality, to know how well my system is doing, I'm gonna need some notion of the truth or judge. Anybody took a machine learning class or data mining class? How do we evaluate machine learning results? We test it on a test set, but we need to know, to have the answers on that test set to know, okay, how well it worked, like labels, sometimes called, right? Same thing in here. If I want to evaluate my results, I need somebody to look at those documents or links or whatever I'm producing and tell me, are they good or not good? All big companies, Microsoft, Google, IBM, Apple, have a huge quality QA, quality assurance department, right? Because they need to know, okay, how well are we doing? This is obvious in manufacturing. When you actually manufacture a physical object, like a phone, you want to have QA to not ship those phones that are defect, right? They still do, they're broken, but in principle, you want to catch the defects before you send the phones. It's not so obvious in here, if I'm Google, how often do I need to check the results and how do I check them to figure out if my system works. Okay. So in this big pipeline, if you like, we're not going to start in here. There's another step here. I'm going to write it. I'm going to say crawler. That's very specific to the web. In general, we can call this a collector. From data source to the index. Indexing is how do we organize this data, but to get it, we need another process there, a mechanism that gets me the data, right? It's not obvious if I tell you, okay, go ahead and index the whole web, right? How do you do that? Now, it may be that's a small collection. If I work consulting for a small company and they only have 2,000 records, crawling is not a problem. They're just going to give me those records somehow on a text file, on a CSV file, a JSON file, whatever. I'm going to have to parse that file. Not a big deal. But usually, information retrieval, this is a process that has to happen efficiently because data is big. Okay. So where are we going to start? When I say module 1 here, what is that? On this board here. Retrieval models that talks about which piece in this diagram.
The scoring function.
Right, we're going to start here. We're going to say, assuming we already have an index, which is not quite true, you're going to have to create the index, but you're going to use an indexing platform, so it's going to be easy. You're not going to have to deal with you know, how internals of indexing work for now. You're just going to call certain APIs and use Elasticsearch as a platform to do the indexing. So assuming that's happening. And then where do we get queries? We can ask the queries ourselves, right? Type random words, see what happens. But that's going to be hard to evaluate and so on and so forth. So I'm just going to give you some queries that are appropriate for these documents that we're indexing. We're not indexing web documents for now. These some nicely formatted TXT documents for which we have the queries and for which we have the truth judgments so we can evaluate them. So the first part is going to be here. That's module 1, 6 days, 9 days. Okay. Then when I say indexing module 2, where is that? That's going to be right here. We're not going to use Elasticsearch anymore. We're going to create our own index. Right? And then when I say crawling, module number 3, that's going to be here. How do we go on the web and collect documents to pass into an index? So a little bit more admin here. In this homework number 3, you're going to have to work in a team of 3. We like teams of 3, but we'll accept 2 or 4 if 3 is simply not possible. Okay? So I think you should think about that now. In the regular term, there's about a month to figure that out, but in the double speed term, there's only 2 weeks. So you have to look around and say, okay, how do I get two other teammates to work with me on the crawling part? What's going to happen, we're going to set up Elasticsearch, the indexing platform, in a way that your three computers connect to each other. And then when we do crawling, I'll give you the what's called URL seeds, where to start crawling. Because we don't want to crawl at random. We're not going to crawl the whole web. So then to do something useful, we'll crawl from some links that I give you to crawl. And I'll give you, if you three are a team, everyone will get different starting points, but on the same theme, so that we crawl documents in common. You're going to be crawling for module 3, maybe 80,000 documents from the web. So that's important to do efficiently. Why? Well, yeah, efficiency is not graded. It's going to make a big difference whether your crawler works fast or not, because you have only 5-6 days to do it. So if you write a bad crawler, that's not going to finish your 60,000 documents. So you need to think about now, starting today, of a team. Who will be my teammates? We're not going to accept single people, no matter how hard it is. I'm single, I'm getting divorced, I live out of town, and I can't meet anybody, and I hate everybody, and I'm not supposed to be here. It doesn't matter. You cannot be single. Okay? We'll accept 2 and 4 if we have to, but we like teams of 3. So I won't go through the whole schedule, but I will go through 2 more things. Once we have crawled, we're going to talk about what's called a link graph. That's very specific to web data, because the web documents are not just text. They text, of course, and text is what matters. When you search by keywords, you primarily mean give me back the documents that match those keywords. If I query for nuclear bomb, I really mean I want documents that talk about nuclear bombs. So that's a very textual match. But web documents contain what other than, I mean, of course they contain pictures, but in text, what else they contain? Web links, right? So this whole module here, link graph, is to try to tackle a little bit the links. Why are they important and how that works? I think most of you heard of PageRank, right? That was the initial Google algorithm for how to deal with how important is a page. Other than matching the words, of course, if I say nuclear bomb, I mean documents that match nuclear and bomb. But out of those documents that have nuclear bombs, some will be much more retrievable or useful to the user than others. So by looking at the links, Google came up with this algorithm, PageRank, to kind of judge the importance of a page independent of its content. Just importance because it has many more links to it. Right? Turn out that this PageRank is actually more of a buzzword and a PR stunt than an actual improvement to Google's search results. But nevertheless, it's something useful to look at. We're going to look at much more than just PageRank. There's several algorithms that deal with how to look at a link graph. And finally, not finally, there's 3 other modules going, but for now, this IR evaluation is where on the board? Right here. So we're going to talk about how do we measure quality in information retrieval. Now you're going to use evaluation even in the first homework, but you're not going to worry about how it works. I'm going to give you a script, and the script is going to produce results for you, and you're going to have to wait until module 5 here to understand, okay, I see, that's what this metric does. Just one thing about this. Why do we need other measures? I mean, I'm sure we know things like F metric, right? And accuracy, maybe, or confusion matrices. Why not use those? Again, let's recap the pipeline. I have an index with, say, 100,000 documents in it, or 1 million, or 1 billion. I'm looking for the words nuclear bomb. I type there nuclear bomb. That's my query. Queries match to the index with a scoring function. Let's say a simple one. I get a list of results. Scoring functions in Retrieval provide a score for each item in your index. So then we usually rank those items, right? Everybody knows that if we put a query on a web search engine, I get back a list of URLs, right? I can click on them and see the URLs, right? So why not use accuracy? Like in machine learning, right? In machine learning, I do a test. I have, say, a bunch of documents or images, whatever I'm doing, right? And I measure for each one of them if my prediction was right or wrong, right? And I count how many things I got right versus how many things I got wrong. And suppose I got right 75% of them. I'll say accuracy is 75% or error is 25%. You guys follow me? Hands up, who's following? Okay. Why not do the same here? If I have those truth judgments, presumably I know in my index which documents are about nuclear bombs and which ones are not, right? That's what truth judgments are. I type the query, I run my system, I retrieve them. Now I know for each one of them, is it about nuclear bombs? Let's call that a yes. Or it's not nuclear bomb, let's call that a no. Why not compute accuracy like in machine learning?
Because there's not a definite yes or a no. A document about nuclear bombs could be linked to something like a World War II. So you can't say that any information it has fetched is definitely accurate or inaccurate. It could be in some way related to what we are asking.
Okay, so this is not the answer, but he has a point here, which I'm going to get back in a moment, where it's a point in general in data science when somebody says, is there a tiger in this image, right? Yes or no. People label that yes or no. And I think his point is, yeah, are you sure? Like maybe there is a tiger, but you didn't see it. That seems funny about tigers, because tigers are easy to see, but for some things are really like borderline. So I think one point that he wants to make here is that when we talk about truth, do you really have the truth exact or not? The other point is that when I do the matching, in information retrieval, matching is a much more loose notion than in other data sciences. When we say match, we let it vague, like it's up to you to define what match means, okay? It's not like in databases where if you say match this field with everybody whose phone starts with 617 and salary is at least $100,000, it's going to return exactly those records, for sure. In here, match is a vague term. Maybe I think that's what he meant. But let's say for right now, I have both of those nailed down perfect. The matching is well defined, and the truth is 100% accurate. AKA, if I say nuclear bombs, if my query is nuclear bombs, this truth judgment set, or collection or annotations, they exactly tells me which documents are about nuclear bombs and which are not, and it's only two possibilities, and my judge set is absolutely perfect. Let's assume that. Can I use accuracy? I'm back to my question of accuracy. Why not use accuracy?
So if you're true, the accuracy is based on just the mention of the string nuclear bomb, then you're always going to be 100% accurate because it's always going to retrieve all articles that have the string. But then it's about relevancy. It might be, like he said, it might be an article for some completely something else which might have a mention of the string, but it might not be about the nuclear bomb itself.
Yeah, you mentioned the same issue as him. That's okay to think about that, but that's not what I'm thinking about now. Let's assume that the world is binary today, just for this example. So the documents are either about nuclear bombs or not. And my set of answers is perfect. So let me draw a visual here. My retrieval results is going to be maybe a list organized by this scoring. It doesn't have to be a list, but in retrieval, most of the time, it's a list, right? So suppose I have a list of things here. This is all my stuff that came out, right? Those are documents. And the truth judgment tells me what? Which one is about nuclear bombs? Which one is not about nuclear bombs? Again, the world is binary, and I'm assuming those annotations are perfect. They're not mistaken. So let's call them yes or no, and say this yes a yes, this is a no, this is a yes, 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 no, no, yes, yes, no, so on and so forth, right? That's it. Again, my ranking function is probably a scoring that score I'm ranking by it. Ideally, what would I like to see here? What's the best result I could get?
So you would like to get the document that you're looking for first?
Yeses to be up
Yeah.
and no's to be down, right? That would be the perfect ranking. I'm assuming the world is binary. I know I could have a document that's marginally a yes and some that's a perfect yes, right? But in here we talk binary. So now that I don't have that perfect answer, there's yeses with no's. Can I measure accuracy in here? I need to do something to measure accuracy, right? Accuracy in machine learning, you got to make a prediction, yes or no, and then you compare your prediction with the truth. And the best result is all yeses are yeses, or all the no's are actually no's. If not, you have errors. In here, I don't really have a classification, right? I didn't predict yes or no, I just produced a ranking. That's what Google does, or Yahoo, or your favorite, right? It doesn't tell you which one's good and which one's bad. It doesn't come up with a prediction saying, I think this document is what you're looking for. It gives you a ranking, and you can go through the ranking if you don't have the truth. You can go with your eyes and say, aha, that's good, that's no good, that's good, no good, yes, no, yes, no, yes, no. Back to my question, can I measure accuracy here? What do I need to do to measure accuracy?
Prediction.
Hmm?
Prediction.
How do I make a prediction out of this?
Just say one result out of it.
I get the first one, and I say that's a yes, and I don't do anything about the others? I could do that. That's I'm feeling lucky, right? I'm feeling lucky. It takes the first one, and it doesn't say anything about the rest. It just says, I'm feeling lucky.
So wouldn't you typically want to measure like the accuracy at different levels? So like the accuracy at the first, like whether the first document is correct, whether the first 5 or the first 10.
Okay, so he's talking about truncating this list, and I can truncate it at different levels. So let's take at 5. I can truncate at 5, or what would be a natural cutoff for truncation in the way web search works. Why?
Easier to see than for
The first page contains 10 results, right? Always. So let's say truncate at 10. That's around here. And when I truncate, what is my implicit prediction here? When I say truncate at 10, implicitly I'm saying the top 10 are yeses and the rest are no's, right? And now I can apply accuracy like in machine learning. I can say, okay, how many are those correct? How many are those correct, right? Yet accuracy is not good. Still has a problem, even if I truncate the list. What is the problem with accuracy?
Sensitivity and specificity, as in
What?
sensitivity and specificity,
Okay.
precision recall.
Right, so before we get there, I mean, I'm not going to talk today about precision recall. We're going to wait for module 5 here. But the problem with accuracy is that it's not a good measure for very skewed classes. In information retrieval, and specifically on the web, for most queries, the number of no's overwhelms the number of yes by a big margin. We're talking about 99.999 no's, right? Take nuclear bomb. How many documents on the web are about nuclear bombs versus how many documents are not about nuclear bomb? Easily 99% of the web is not about nuclear bombs, right? Perhaps 99.99. So if I measure accuracy, what's an easy way to get a very high accuracy?
Make sure everything.
Predict no to everything. Because the classes are so biased, if I predict no, I'm going to be right 99.99% of the time. For most queries, most of the documents, as in a vast, vast majority, are not retrievable or not relevant or not good, right? And then I get very high accuracy if I just say no all the time. So people have realized this before information retrieval. They have realized that when ranking is an issue, we probably don't want to use accuracy. We want to use other things. Now, I don't want to continue with this. I'm just saying that's why we can't just take measures from typical data mining or machine learning and apply it verbatim. We need to come up something with precision, recall, rankings, average precision, all kinds of numbers. But before we get here, we're going to need evaluation for homework 1. I'm just going to give you a script, tell you look for that number, and when number's up, you're good. Okay? So we should stick with this picture. This picture is about 5 modules out of 8 or so. The rest, what's not in here, it's all kinds of interesting AI applications. This has been the story for many years about when Alta Vista came along, 90s or so, web started. This was the picture. How do we organize the data? How do we, a big problem early on was how do we update the documents? It's not enough to crawl once because those documents might change next day or next week. And now my index is not correct anymore. So how often should I update? I'm Alta Vista now or Google, right? And I have the whole pipeline in place. I have an index. The problem is people are changing their web pages all the time and I'm still retrieving data from my old index. So I'm trying to update. But I suck at algorithms because I'm Alta Vista or Google early on. So my update takes a month and a half to update. So I'm retrieving documents from like 2 months ago. So how good is Google now? How often things get updated? A day. Right? Updating in a day, all documents that change in the world, or most of them, they work in tiers. So tier 1 is 1.5 billion documents. That's a major, major engineering feat to do such a thing. Even for Google, who has a lot of money and a lot of computers, updating on a daily basis the tier 1 index, you know, the documents that get hit all the time, that's not a small job. So that requires a lot of infrastructure and algorithms to do so. That's what made things possible, that scale. When Google came along, I think 1998 or so, for the first 10 years, he couldn't move because of the algorithms and infrastructure, and then out of a sudden things exploded. So the rest of it, after module 5, I would say up to 5, that's the basic IR, indexing, crawling, evaluation, scoring, so on and so forth. After that, we say, okay, now that we have an index, what other things can do with it? There's a lot of AI that's going on related to those indexes and documents in indexes. Machine learning is the obvious application, but there's clustering, there's robotics, there's AI, there's data patterns, people patterns, selling ads, being adversarial, you know, like creating all kind of fake links and spamming. All of that is based on some AI on top of the existing infrastructure. It's a chicken and egg problem in that the bad actors are trying to take advantage of the infrastructure to make money, of course. While the good actors, say Google, are trying to fix the infrastructure so that the bad actors don't take advantage of it. So when we get to these modules, we're going to talk about things that are quite funny. If you, I don't know, maybe too young for that, but there's famous Google bombs that people created certain queries or certain link farms to, based on existing infrastructure that was at the time, to create a very different list than what you'd expect of results. And then Google fixed it, and then those people, again, took advantage of that infrastructure. It became a back and forth between the main AIT companies and those bad actors. In fact, maybe you'd be surprised to know that 80% of the Google engineering today is fighting the bad actors. 80% of the entire Google engineering effort is to how to fend off people who try to take advantage in an unfair way, making money by creating adversarial effects, both on Google infrastructure and on people. Because if they spam you, even though, say, your hard drive has enough space and your email has enough slots or whatever, just the time it takes to deal with the spam today, it's a major problem. For individual people, not to mention companies or schools or hospitals that have to do data protections and other things. So about 80% of the big IT companies today goes into how to protect ourselves for bad things happening or adversarial things happening. Okay, so that being said, let's start this. Let's talk about the first module. why do we need an index? Why not use a database?
Faster accessing.
Hmm?
Faster accessing within it.
Faster access? I'm not sure. I mean, I don't know anything about databases, so very little. But I think databases are quite fast, aren't they? I mean, did anybody notice some slowdown on database, like in, say, Oracle or MySQL? I'm asking honestly here. I don't think databases are particularly slow, but I don't know much about it. Maybe they are slow. Are they slow?
They also have indexing.
Hmm?
They also have indexing.
Right, they try to catch up because they can't sell anything, right? So the last few years, all databases put a lot of effort into indexing, right? Because they can't deal with text. But what's the issue with indexing? So let's imagine ourselves in a toyish world, right? If I have a lot of documents, say you're gonna have just in homework 1, 85,000, and this is a toyish data set, like it's not real. There are 85,000 documents, and I say, I want to look for the word Virgil. That's my name. How do you do that? How do you look in 85,000 documents for the word Virgil?
Well, if every document was the same, it'd be very easy to use.
The same as in identical?
As in they all have a name field, like they all have a name.
No, they just text. So the document, each document has an ID, document 1, 2, 3, and a bunch of text.
Then it'd be really hard because document. Then you would have to look through every document for your parameter. You would have to search, which will be very long because there'd be nothing on the document.
Right. So you have to go through the
Using
text, and when you see Virgil, you mark it. I've seen Virgil, right? I mean, there's no way to avoid going through the text to see if you find Virgil. Okay, fine. But if I want to look for Virgil and separately, not together, for nuclear bombs, right? Do I have to go twice to the text, or can I just go once? Right? But then I have to keep track of Virgils and nuclear bombs. What if I want to go just once, but be ready for some query in the future that I don't know? Right? Is there a way to, I don't know what queries he's going to ask next, but is there a way to process the data in a way that I don't have to, for every single query, go over and over and over again?
Just take each word in every document and then just have a mapping of this word appears in these documents. And so then at search time, you just go to that row and you get those documents.
So that's a very basic idea of indexing. The way we want to look at that idea is to say, this is a document term matrix. So the way we could imagine this is similar to machine learning feature matrix. I have document 1, document 2, up to document 3, up to document n. Say I have n documents, right? And then I have word or token. Let's say word because it's not the actual version. Word 1, word 2, word 3, up to word, okay, well, let's say D for dimensionality. So what the basic indexing does is to take the text, these n documents that I have, in plain text. I'm not talking about the HTML or fancy, just plain text. And to create this matrix in one pass, and then store this matrix in a very convenient way to access. What people have observed very early on, before information retrieval, is that if I'm looking for queries that are based on keywords or words, if I'm looking for this word, I want the data organized by word, not by the document. All the documents come organized by documents, right? Whether it's an insurance company, or web documents, or medical records, or songs descriptions, or movie ratings, whatever. They come like movie 1, movie 2, movie 3, or text 1, text 2, text 3, record 1, record 2, record 3, right? That's how data comes. But what people realize is, wait a minute, if the queries I'm going to have to serve with my system here in the scoring function are based on those words, like nuclear bomb. Nuclear might be here, and bomb might be here. Then I don't want to read the data by documents. I really want to read it by the words. So, as a basic notion, the indexing is going to try to create this data and store it in a very convenient way. So then we can just say, I'm looking for the word nuclear. Give me what you have for that word, whatever documents, counts, positions are in there. And then I'm looking at the word bomb. Give me what you have in there. I want to know what documents contain this word. And then I have to do some processing because I'm looking for two words. How do you want to treat those two columns of content? Do we want to ask for documents that contain both of them? Or do we want to sum up the results? There's got to be some processing between, okay, you look for a word, here's a list of documents for that word. You look for another word, here's a list of documents for that word. Okay, how do you want to process those two lists? We'll get there. But before we do, what's the problem with this matrix? Like that. Like if I say, okay, write it down.
Space.
How many rows we have here? 100,000? That's for just homework 1. Imagine if you Google. That n could be 100 billion, right? How many words do we have?
300,000.
Huh?
300,000.
Depends in what language, right? But let's say English. We only going to do English in this class. How many words are in English language? 300,000? Common English. I don't think it's like really 300,000 common English. I mean, if you really look at the whole Wikipedia, yeah. But in common English, there are not that many words. I think it's 50,000 that's common, 100,000 if you include fancy words now. And it's, if you really index everything, you might get to 500,000 or a million. But even if we have just 50,000 words, how much is 50,000 times 100,000? Just homework 1, right? This is a very toyish example. How much is 100,000 by 50,000? 5 billion? So obviously there's a problem with this matrix. I mean, conceptually that's what we want, but we need to store it in a good way and access it in a good way. Right? So he was right, and I'm sure you knew this from before. I need to store it not from a document's point of view, but from the word's point of view. And that's going to be very sparse, this matrix. Most of these entrances here are be NA or 0. By the way, what would be a default entrance to put? What is this cell here? What should I put here? Count or positions or both. I can say count would be how many times this word appears in that document, right? And if I'm not happy with just the count, I can also put the positions. That word is in position 7, 25, and 55. Or if I want to do something very simple like Boolean search, I can just put
Yes or no.
yes or no, is that word in that document or not? 0 or 1. But whatever we put, this matrix is going to miss a lot of entrances, right? It's going to have zeros almost everywhere. The reason for that is most words appear in very, very few documents. I just made this case earlier that the word nuclear is a very rare word. Less than 0.1% of any collection will contain the word nuclear, and same thing for bomb. But there are some words that are actually very, very frequent in text. In fact, they appear in all documents. Like the, of, about, things like that, right? So the bad part is that they will be extremely popular. The good part is that we probably don't need them. Those words offer no content. They're just grammatical constructs of the language works. Like in the second grade, you miss a the, you lose a point in your thing. But in actual web search, people don't even type the, right? How many, do you type a the when you put a query? No, and because all those things are out anyway, so we can skip those. Okay? We just make a list of words that we think are just grammatical constructs, stop words called, and just ignore them. Or we can be intelligent about the problem with ignoring stop words, making a short parenthesis here, is that end is a stop word, right? The word end. But in certain constructs like bread and butter, if I take end out, I don't have that construct anymore. No is a stop word. Most people think no is a stop word. But know something offers a different semantical meaning than just that something alone, right? Waste of time, if I take out off, has now maybe a different meaning. So I think in principle the idea of taking out words like stop words because they're frequent, they offer no content, it's a good one. We got to be careful that for some purposes, stop words might be useful. Okay, so back to this matrix. That's what indexing does for us. And we're going to use Elasticsearch first. Elasticsearch is a very efficient indexing system and very useful to know, like I said. So it's definitely worth the time spending time on it to figure it out. I should say that a lot of people end up with this class in the past, and the biggest benefit they had is learning Elasticsearch, because I got the feedback from them, hey, because Elasticsearch I got my job, nothing else in your class was useful, but I got the job. No, they didn't say that, okay? But that's what they meant. They meant, wow, that thing with Elasticsearch got me the job I wanted. I don't remember what you did after that, but so it's very, very useful thing, okay? Now, because it's so big, it's gonna take you a little bit of time to figure it out, and the TAs are ready to help you with those things. I would recommend you to start as soon as possible, just understanding how the basics Elasticsearch work. In fact, TAs will come here in an hour or so, and we will give you a quick demo, if you've never seen it, how to install it and run it. Since I'm not quite done with the intro, I say here Java or Python. So I'm willing to let you do whatever you want for programming. The assignments don't specify a certain programming language, so it tells you what to do and you can do it in any way you want. But we're not going to support every programming language. We're going to support Python by default because it's by far the best language to deal with this stuff. We're going to try the best we can to help you in Java, and I'm not sure about other languages. If the TAs know the question you have in C# or whatever, they'll answer, but they are not required to. Some languages will be forbidden, like C++. Okay? In this class, you cannot use C++. Now, I'm not saying C++ is no good for information retrieval. In fact, most of Google stuff is written in C and C++. For efficiency purposes, once you know what you want to do, you always have to go down to a very low-level language. That is true. But in this class, starting with C++, it's going to be an absolute nightmare. Plus, me and the TAs, we don't know C++ anyway. I'm a mathematician at heart, so I'm much better at numbers and math than at programming. So most of the questions about programming will be the TAs that help them out. Okay. So what do we need for homework 1? I tried to make the schedule fit into, I took the schedule from last year, make it fit into 7 weeks. So here's what I got. Homework 1 due in 9 days. That's 11. Homework 2 due in 8 days. Homework 3 due in 7 days. Then homework 4 due in 4 days. That's an easy one. We think. Then we have what? 6 days, right? Then 5 days. I mean, you really have to know machine learning to do these things that fast. The good thing in here is that you're going to use libraries. You're not going to program your machine learning algorithms. You're going to call liblinear or SVM rank or whatever. So you have to be familiar with calling those things in and out and understanding results. But you're not going to program your support vector machine. So you're just going to use packages. That's why they can go very fast if you know what you're doing. Another 5 days or so. Realistically, we may have to drop one homework. I'm thinking that it's just gonna be too ambitious to do 8 homeworks. But I'm gonna tell you right now, we're not gonna drop the 7th one. So 7 are guaranteed. This class, it's conceptually much easier than other things you took or you will take like algorithms and machine learning. So let me show you what I mean. homework 1, the basic formulas are just fractions with multiplications in them. This is like 6th grade, intellectual level, okay? You're not gonna suffer in this class because it's so hard to understand. Like, you know, when you go home with algorithms, and you're like, how does this work, right? Like, I can't get it, right? That's not gonna be the issue at all in here. The issue here is gonna be, you're gonna be out of time all the time, okay? Because hands-on requires a lot of kitchen and infrastructure and figuring out how to do things, and just Googling of how stuff works, it's gonna be tough in 5 days. So the grade, the reason not everybody will get an A is because some of you will not finish those homeworks. That's what's gonna differentiate the grades at the end. We didn't have an exam before, and I don't think we're gonna have an exam now. I'm not promising that. But I do not think we're going to have an exam. I'll make a decision about a few weeks from now about that. I don't think there's time to schedule an exam. Okay, so homework 1. Where is homework 1? Homework 1 is in here. But that's the easy part of homework 1. Because if you look at those formulas, those are all different, like 5 or 6 formulas for how to do this. These formulas are nothing. This Q stands for what? Query. And D stands for? Document. So this scoring function gives you a score between a document and a query. And once I have any scoring function, I can produce a rank list. And once I have a rank list, I can evaluate it and I can figure out how good it is, right? The problem in this homework is to get those ingredients for the formulas. Like the TF. What's TF? Of W, what's W? Word. And D? And TF?
Term frequency.
Which means count. TF stands for term frequency, aka count. So, TF should be accessing that list here, right? If I say I have the word is nuclear, I'm going to get through all the list and find out where nuclear is. So that should give me the TF on all these documents. If I do it efficiently, I'm only getting a list with the non-zero TF values, right? Because in every list we say there will be a lot of zeros except for the stop words. So we don't want to return for every word a list of 100,000 documents if only 3 or 4 of them contain that word. We only want to return those 3 documents. So that's what indexing does for us, organizes this data. If I say, give me the documents that contain the word nuclear, only retrieve a list of like 3 documents or 4 documents. And that makes it much more easier to work with. Now, Elasticsearch is based on a very well-developed indexing platform that's publicly available called Lucene, Apache Lucene. If we would use Lucene, which was at the other sections of information retrieval in this university do, they use Lucene, this would be very easy getting the TF counts out because Lucene is the underlying infrastructure. We're not using Lucene. Will make a little bit more difficult getting this basic information out, like TF counts, just because I think the advantage of knowing Elasticsearch down the road worth the extra effort to go into how to obtain TF counts. Elasticsearch doesn't offer an immediate way to get the TF counts, or it didn't last year. The TAs will walk you through ways to get those informations out easily. We're not going to use the latest version. They will tell you what versions they want you to use because that's the one that they know how to use, okay? You could use the latest version. It says latest version is 6.3 maybe. You can use the latest one, but kind of if you are on your own, I would say use the one that TAs are using so that all the scripts are working. So that's going to be your primary problem, this homework. How do I index the data and access easily all the ingredients? TF is one of them, but there's other ingredients in those formulas, like DF and IDF, and this looks bad, but it's not so bad, this one. Everybody heard of BM25 before? Yeah? How many people? BM25, hands up. 1, 2. BM25 was an idea that came from a very fancy theory, something with probabilistic, retrieval model, blah, blah. It came down to a very simple fraction, really simple. And then people have complicated it because the theory didn't really work in practice. So they keep adding things to it, trying to fix it and fix it. And that's the formula for a few years ago. Maybe now it's even more complicated than this. This is going to be a theme throughout the entire course. Theory, that sounds very good, not going to work very well. Okay? So your job is not to learn the theory or give me back the theory. I'm going to be in here explaining the theory, but you're going to go home and say, okay, that's not going to work. So how do we make now this work? No, I'm just kidding. It's not that bad. But this is really a theme in the information retrieval that to make things work, especially for languages, because we're talking about data here that's text. I'm going to talk about this in a second in detail. Whatever seems like theoretically very palpable, like people have used scale distance, they have used information theory, very fancy models. It doesn't really match how people write text. Most text is written by simple people who use basic language construct, who use expressions they have learned from their parents or they have seen on TV or things like that. How many expressions in English use words that have nothing to do with what they actually want to say? Like the word itself doesn't match the meaning. Because of all these expressions, theory sometimes doesn't work very well for retrieval. Now, text has a particular well-known problem that's a big AI unsolved problem, which is featureization of text. You can say that's a feature matrix, that's my objects, those are my features. It's a well-known unsolved problem, as in, I don't know what matters for where in order to classify or rank text. What I mean is this. If I tell you I have data in an image, a machine learning algorithm can decide based on data, on the features that I have for that image, very accurately what's in the image. And that's why deep networks that are very popular today work very well on images. Why deep networks don't work very well on text? Only very recently, if you paid attention, I don't know how many people know what I mean by deep networks. Hands up, okay? So very fancy machine learning mechanisms there. We don't need to know what deep networks are. Only about 2 years ago, they've started being implemented in commercial systems. Why is that? Why is it that simple machine learning algorithms don't work very well with this kind of features? Let's give somebody else a chance. Yes?
Because they're sparse.
Sparsity is true. It's not easy for things like regression to work on sparse models, but we've solved sparsity in machine learning. So that is true. Simple model regressions don't do well with sparsity, but we managed to solve that problem with gradient boosting trees, for example. So we would have models that would work well. Yes?
Deep networks, because textual information is best conveyed when it's in a sequence, and deep networks help in using that sequential information during predictions.
Okay, so that is true from a technical standpoint. What his answer is correct. It wasn't until the networks could understand not just the features, but the sequence of words. Sequence turned out to be very important for the actual meaning of text. It's not enough to say what words I have and what counts. It matters the sequence of text. If I change the sequence of words, I may change the meaning. If you notice in this matrix, which is called a bag of words representation, I don't have, assuming I don't have positions, I don't have the sequence, right? I only know what word appears in what document how many times. That's a bag of words. It turns out that a lot of the text meaning cannot be obtained directly just from the word counts, which is not the case for songs of images. For songs, if I match certain, say, piano patterns or violin, and for movies, if I match actors and genres and so on and so forth, I could pretty well identify or predict what this movie is going to do. But for text, I can't. It works for certain queries. If I'm looking for a location, if I'm looking for a phone number, if I'm looking for things like that, a very, very, say, navigational query. I want to know what's the address of Hilton. That's easy to get, you know. But if I try to match a textual meaning. Suppose we had this project before, very difficult, I think, political discourse. All the politicians, they talk about the issue of the day in all countries, right? In this country now, everybody talks about immigrations and baby cries at the border. By the way, I'm not into politics. I'm neither Democrat or Republican. I don't like or dislike any politician in particular. I'm just saying in politics, if you take what people say from both sides of liberal and conservatives, right? And you map into bag of words, you get the same bag of words for everybody. Everybody talks about the same terms with same frequencies. And now, which one is saying that, say, I don't know, make harder the immigration laws, and which one is saying, no, make them easier. That's hard to do with just bag of words because there's the same words with the same frequency in political discourse, although the meaning of what those people are saying is very different, right? So these are some examples like this of obvious where you have to parse long, even short sequences of text will not be enough to identify the difference, right? You need long sequences of text to identify, okay, that's probably a liberal politician and that's probably a conservative politician. Actually, political discourse is very hard to predict. There's many research effort to try to, okay, here's the document, do you think it's coming from a liberal, from a conservative? Hard, particularly because of this problem. So because of text have these features, at some point we're gonna get into what does relevance mean? Not today, later on. We're gonna be like, okay, I'm trying to match these documents with these keywords. Do they match verbatim? Like I can tell these words are in those documents or not. Or do I try to do, that's called syntactic matching. Or do I try to do something semantic where I'm trying to figure out the meaning of the query versus the meaning of the document. So part of the later AI tasks, like say topic modeling, gonna try to get into those things. Topic modeling, have a way to match documents, to put them into sort of concepts, and then to try to match that concept, even though I may use different words in the query than the documents have, as long as they're on the same concept, maybe I can do that sort of semantical matching. Okay? So back to homework 1. The part that you're gonna have to do before you run the models is to get the data, put it in Elasticsearch, plain text. It's written in here somewhere. Right? Document indexing. And then make sure you get all the ingredients out of Elasticsearch in an efficient way, so then you can run the scoring functions. The scoring function, once you have one of them, suppose you build this one, and you rank based on this function, you obtain a list of results. By the way, the list of results have to be per query. I'm going to give you 25 queries. So the list of results would include a certain number, say like 1,000, ranking of top 1,000 for each query. So if I have 25 queries and 1,000 results per query, I'm going to get a list of 25,000 documents organized per query somehow. Once you have one, it's easy to do the other and the other and the other. Right? Let me show you how that looks. Try to make this bigger. In the homework, it's written that you have to present the results, you have to put the results on a hard drive in a certain way. This is the way. So let's say something that you're going to have is this. This is a certain format required by the evaluation script. The first column is the query ID. So that happens to be query 89. Q0, it's just Q0 there. I don't know. Somebody who wrote the script put Q0 for some reason. I don't know. And then it's there. You don't have to worry about that. This is a document ID. Document IDs are going to be clear from the data. When the data comes to you, there's clear what's a document in there. This is a ranking 1, 2, 3, 4 up to 1,000 for that query. This is the score that your scoring function produced for that document and for query 89. Now this will be different for different scoring functions. Your homework one asks for 5 scoring functions. This is the called okapi one, I think. Right. So okapi is one of my scoring functions. A different file will have VM25 scoring function. And this in here is an explanation that if you want to put a comment, you can do so. I choose not to. So I have this file, and I think you can see here that query 89 goes to the rank 1000. And then I start a different query. Right? So it's a ranking of the first 1000 documents, 29, and 1000. We can look at those queries, I think. Let's see if we... I think we have the queries here. They are in, I forgot where they are. The zip file, okay. So let me see if I have that here. Oh, it's so those are the queries. They come with a data file. So each query has a ID and a description. These are from a conference that's dedicated to information retrieval. It's organized by the US government, Department of Commerce. This is data, all data. So the latest data sets used by this conference are much more fancy than this. They, however, at this point, they didn't realize how hard it is to deal with non-keywords queries. So you can see the intent here is to describe something like you describe to a person and to try to match that query, which actually makes it harder. The first thing you'll do, you'll have to strip this query on everything that you think is not content relevant. Document will describe, I would cut all those words from the query, because neither one of document or will or describe has something to do with matching that word. You're not looking for the word document in the documents that you have. This is just a way to state the intent of the query. So there's a difference between the intent of the query, which makes sense for a formal statement, versus what words from this query should I actually type in my retrieval system to get back relevant results. So document will describe one or both sides of the controversy over the use of standard of performance, determine salary level, blah, blah, blah. Which words should I use as keywords that I think are gonna get me good or relevant? Yes, documents. So that's something that you, I think, will have to do manually for homework one at least. It would be nice. I think it's a difficult thing to do it automatically, because for some words, how do you decide automatically if that's a word that has content value or doesn't have content value? This notion is very contextual. The word document is not a stop word, but in this context it is. We don't care about the word document here, right? So I'll say take manually this list and reduce all the queries to only the words that you think are relevant, and put those words in, see what happens. Yes?
Can we use something like inverse document frequency for WFS?
Yes. So that's, I'm gonna get back to the retrieval models. That's part of this formula. Some of these formula scoring functions include IDF, inverse document frequency. Some do not. But even with that, inverse document frequency will not take the word document out. Will take a stop word out, but not the word document. Because if you look at the whole collection of text, the word document is rare enough that the IDF will still count it in. So what he means by IDF is, wait a minute, some words are more important than others. I say take out manually the ones that you think are no value here. That will include both stop words and the word document. He's saying automatically IDF can do this for you to some degree. IDF is a way of ranking or weighting words. The more rare the word is, the more important it is. The assumption that a very frequent word does not have content. That's certainly true for stop words. But there's some words that are in between, so IDF it's a continuous scale of very frequent words that have low IDF weight and very rare words that have high IDF weight and everything in between. I still think in here, some words may appear high IDF, but in fact they have no content value for these queries. So these are the queries. What's going to happen with, how do I evaluate the system? So I can write a command line here. I can say, this is program, Retrieval, right? That requires -q if I want to see all queries, a curl file. A curl file is the truth file, the judgment file. So I think I have one here, and then I can evaluate that result I showed you. So this is saying evaluate that list of results I just showed you for all queries using that truth annotation file, curls, da 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 da. If I do this, I get back answers. We're not going to understand those numbers until module 5, but this is the number we're looking for, average precision. I'm not saying it's difficult. It relates to what you were saying. If I cut the rank list at different levels and I kind of average those levels, but not all the levels, we have to get to module 5. This is the number we're looking for. The TAs will give you a minimum threshold. They'll say, for all those 5 models, you are required to get at least blank in here and at least blank in there to count as good. So this is easy to run. It's a simple program. You can read it, but you don't need to read it until module 5. Of course, to run it, I need the curl file. That is the answer file. So how does that file look like? That file has a query ID. Those are the same IDs that you've seen in the query file. A document ID and a binary 0, 1. 0 stands for no, and 1 stands for yes. This is a binary world in Bookmark 1, so there's no gradation of how good a document is for the query. It's either white or black. So with these answers, I can evaluate any retrieval list. Because if you give me a document that's not all the documents, that's not for every query, I should have 85,000 documents, all of them in the collection I give you, but there's only some of them annotated. So what happens if you produce a list that contains documents for query 51 that I don't have? What does Retrieval does? Produces a list and says, okay, this document I don't have in my truth judgments. What do I do? We say no. Everything that's not in the list is a 0. Okay? But a document can be no for query 51 and yes for query 68, right? That's possible because a document might be relevant for a query but not relevant for a different query, right? So how do I get this? Where do I have this file? Where in machine learning, where the labels come from? Yes. Somebody must have sit down and answered those things, right? So for some data, this happened naturally. I mean, there's just data in there. I already have all the people's plane tickets with their expenses and money, it's already collected, right? But for some data, I don't have these truth judgments. I'm talking all the data science, not just I have right now. So this could be an expensive and complicated process. For some data sets might be easy, like if the tiger is in an image or not. How do I get somebody to answer that question? Is the tiger in this image or not? I put a CAPTCHA, or I just pay somebody, like a mechanical Turk or some crowdsourcing, right? But what if I have a medical document and it has diagnosis and whatever other things, and I want to know, okay, is this person has diabetes or not? I can't just ask a random person from the other side of the world, right? I have to hire a doctor or somebody qualified to answer that question. That can be extremely expensive. These people did this for the US government conference that I mentioned earlier. That's a conference that's organized by Department of Commerce, and it's at the government location. It's called NIST, next to Washington, D.C., National Institute of Standards and Technology, and they are tasked by the government with deciding how to measure everything. Now, they include scientists, some of them with Nobel Prize in there, but their main job of NIST is to decide how do we measure things, from basic things to length and pressure and weight, to complicated things like text evaluation or trade measurements or economic parameters, right? So some things, we all want to measure things in engineering, in geopolitics, in science, in everywhere. And the primary task of this agency, NIST, is to figure out how to measure things. And say they have this conference that initially was based on, okay, how do we need to measure text performance and retrieval? And they hired for this task, which is very tedious, because in text it's not like in an image. In an image, anybody can spot a tiger, right? In text, suppose I give you 20 pages, and I'm asking you, is this document about Donald Trump? That may be easy, you type Donald Trump and you figure it out, but what if it doesn't have the words Donald Trump, yet the document is about Donald Trump? You have to end up reading the document. And reading can be a very tedious job if you really have to read everything. So they hired NSA analysts, those people in the Cold War that study all kinds of intercepts and coded messages for a living to figure out if Russians gonna bomb the place. Literally, I'm not kidding. We've been there at NIST as part of my research job, and we sit down with these people, NSA analysts. They are trained to look for hours and hours and hours and not miss a spot into images, into text, whatever. And they have to do a special training because normal people, it's well known, no matter how much you want it, after a while, you're going to lose your ability to spot things in, say, text. You're going to do well for half an hour, but then you're going to start making mistakes. So those people being trained for things like that, they got hired at like $50 an hour to annotate those documents. That's why this kind of list that we have here from this conference are much better than any crowdsourcing effort. But now on Google, I don't have this list, right, for all the web. Like, is it reasonable to start even the process of judging web documents for all the queries? I mean, I don't know what queries. In academic experiments, we have 25 queries, the ones I'm going to give you, and we stick with those 25, and we ask all the systems functions to run on these 25 queries so we can evaluate them and compare them. But if you're Google, you don't know what queries people are going to put, right? So how can you get the QA department running if I don't have these truth judgments?
You use the history of how many times a particular site has been clicked for any kind of query and how much time was spent on that particular site.
So I can use a pseudo annotation that's not really an annotation. It's not a person that really have looked at, and I trust that person to say, yes, that document is good for that query. That's this one here. This document is good for that query. Instead, I say, if enough people click on that document, who put that, enough people who ask exactly that query or very similar, right? Things like I don't know, Brazil playing Mexico, right? How many people put that query today? Few million queries of Brazil versus a few 100 million queries, right? How many people do you think type that query in Google today, Brazil versus Mexico? A lot. Now, if I measure how many people click on certain things and stay there before moving out of that page, that's what you're saying, I get a pretty good estimate of what document is good for them. The problem with this approach is it only works for top documents. In a queries like Brazil versus Mexico, nobody will click outside the top 10 results, right? Because it's a navigational query. I'm looking for an answer here, right? I'm looking for a result of a soccer game. I'm not looking for the history of Brazil. Right? So then people will click on the top 10 documents, and you only have clicks on the top 10 documents. So the rest of 1 billion documents on the web have no annotations. You could say that's okay because the rest of the billion doesn't matter, but what if they do? So Google has, if you go with this approach, there's an exploration versus exploitation problem. Since I know a lot of things about few documents, I can keep posting those documents for every query that people ask, Brazil versus Mexico, because I know they're good, because people have clicked on them, but I won't get clicks on any other documents. That's an exploitation. If I want to do exploration, I want to get clicks on other documents, so every once in a while I put other documents up just to see if people click them. I'll get clicks on those documents, but I'll serve junk to people that get mad, right? So I can use a strategy like this. Or I can get a QA department, which will have to do this job of sitting every once in a while, pick a query. Not Brazil versus Mexico, because that's easy, but more like informational query. Informational queries are queries for which we don't know what kind of answers we want back. Navigational queries are queries for which we know exactly what we want, like a score, a location, an address, a phone number, time to close, things like that. Informational query, I'm typing something like nuclear bomb without knowing what that is. I'm saying, I don't know what nuclear bombs is. I'm just typing here to figure out what it is. I'm thinking, most of us do that, right? Every once in a while, we don't know what something means or what to expect, and we type it just to see what comes back. The problem with these informational queries is that the recall, the number of documents that could have potential good information is much, much larger. If I'm only looking for a phone number or an address or a game result, I only need 1 or 2 documents to know they're good for sure, and then I'll put those. But if I'm looking wide for, say, diabetes symptoms, if I don't know what that is, there could be many documents that are useful for me. So this is a hard job. I said this earlier. It's a hard job to do it at scale if you are a commercial company. And I think you notice that for some queries, Google, even today, they fail quite spectacularly when it's not so hard to get the right answer. They get it wrong. So this is going to be part of our homework 1. It's going to be, okay, once I have a list of results in this form, that's 25,000, 1,000 per query for one scoring function or copy. How do I evaluate it? I could get the other one. Let's run track eval here. I have another one that is results.bm25, or what is this? TF-IDF. That's what the IDF. TF refers to the count. IDF refers to this rarity notion, inverse document frequency. For each term, like nuclear or bomb or diabetes, will tell me how important that word is. If I run this one, I get a much better average precision here. Remember the first one was 0.12, this 0.19, so presumably the CFIDF mechanism works better because on average, this is an average over all 25 queries, but I can go back per query and see how I'm doing for each query separately. If I go up here in the listing, all these results are for query ID. This is query 98. This is query, what IDs I have here? I think this is the query ID. If we look into the query file, you'll see those IDs. So I can see the results per query. Now, of course, some of these numbers can be very low, like I'm doing very bad on that query. So I can focus on some analysis. Why is it that for this query I'm doing badly? And some of these will be very high because they're easy to get, right? Like this one seems a lot higher than the rest. This query 77. Okay. So any questions? I'm talking a little fast today because Wednesday we have no class. I want to give you, let you with something that you can actually start the homework.
So what does that mean? Add 0.00, 0.10?
That has to do with what he asked about truncating.
So why do we have to consider all of them? Why can't we just consider the first 30 or first 50?
We're going to get there at module 5. It has to do with queries that have recall components. Recall means you need to go down the list to find all the information. It's not enough to look at top documents. So how down? That's
So once you start getting really low values, why can't you truncate from there and then calculate average precision?
This is not ranking. This is not ranks. It's something to do with the percentage of yes documents found so far.
Yeah, so
The number we care for homework 1 is this one. Okay, average precision. The how do we look at those ranks, like why average precision, this is the primarily metric that we're going to use, works this way, as opposed to in information retrieval there are many measures, and they all serve a different purpose. Do we have a table here? No. There is at least 100 measures that people use in information retrieval. I don't have that. I think this is the one. I'll find the table. There's at least 100 measures that people use, but for now, I don't want to focus on that. I want to focus on getting a list of results based on a scoring function, and then evaluate with some simple metric, and then we get to module 5, we'll talk about the other metrics. So, to facilitate homework 1, let's go back there. After you get indexing running and you'll be able to extract what you need, what is the actual scoring function that we need? So there's several classes of scoring functions. Normally I'll take a break at the middle, but today I don't want to take a break in the middle. I want to take a break in half an hour, so then we can break it and the TAs will talk about Elasticsearch. What we have here are few ranking functions. They actually into several classes. So let me write here. We have Boolean. That's not part of the homework. It's too easy. It's like database search, Boolean. We have vector space. All this stuff here, for copy TF, TF-IDF, and BM25, those are vector space models, more or less, or variations of them. And then we have language models. Let's call it language probability models. So what we have for the homework is vector space and language models. About 2 and 3, or 3 or 2, something like that. So there's a significant difference between those two classes. Now the formulas in here and in the website, of course, there are all kinds of notes. So I can go into notes and see something to read here. I have the notes with me, but I won't follow them today. I also have slides, vector space models, how they work. And then we have other slides for BM25 and TF-IDF. And then we have more slides for language models. So we're gonna need to figure all this out in like 8 days to get the homework one done. I know I'm insisting on this and I'm doing it on purpose. You guys really have to start like tonight. And you're gonna be late anyway, but because it's way too much stuff happening very fast. So I want to talk a little bit about vector space models today, and language models will be on Monday because they're different. So we have the formulas that's in the homework and the notes, but what's the concept? In a vector space, like here's a three-dimensional vector space, right? Look at the axis. I could have multiple dimensional vector spaces. I'm talking about linear algebra here. And suppose I get two vectors, right? Let's call one of them D and one of them Q. In a vectorial space, or vector space, D has D1, D2, up to D, how many axes I have, or coordinates, right? Let's say big D. That's the number of dimensions. And Q has Q1, Q2, up to QD coordinates or components. In my drawing here, D, the big D, will be 3 because it's three-dimensional. But in a term document matrix, D might be 50,000 because I have 50,000 columns dimensions, right? So the reason I picked D and Q is that I want one to stand for document, one for the query. But this has to do with any vectorial space. I have two vectors, D and Q. So if I use a vector space model for scoring, for concept, what do I want the score between D and Q to be? I mean, we're cooking it up right now. That's what we're doing. What do I want this score to reflect? When this should be high? When should be low? They're similar, right? So high must mean similar. And low must be opposite or non-similar. Okay? So now we use our high school mathematics to say, okay, how do we measure similarity of two vectors? What do we do? When two vectors are similar?
Cosine.
Can use some distance, some notion of distances. And just like with the matrix, if there's 100 matrix for information retrieval, guess how many distances are for vectors? Like easily in the hundreds. So what are the popular similarities or distances for vectors?
L1, L2.
Distance, right? Cosine. Euclidean. So what's Euclidean distance, by the way? So distance, what is it? North 2 or Euclidean? What is that? Between those two vectors, how do I measure the distance between them? I do a sum, right? Of for I equal 1 to D by component. I do DI minus Q I squared, right? And I can take the square root of that if I want to do geometry, because this is the square root of it is the actual length of this thing, right? The difference between them, okay? Before cosine, I want to talk about dot product, because that's easy. Dot product is what? I also do a sum over all components. So I equal 1 to D of DI times QI. I put this I on top to distinguish between coordinates versus indexing document 1, 2, 3, query 1, 2, 3. When I put the exponent at the top, I mean that document component 1, 2, 3 coordinate, like in machine learning. So this is sometimes called D versus Q, like that, right? So there's a dot bracket with a dot in there. Okay. So let's, I know you've been through high school already, but let's figure out how this actually works. What's happening here? when obviously, what's the minimum I get here? It's the whole thing, 0, right? Because there's a sum of squares, so it's 0. When do I get 0?
Exactly.
When all the i's is exactly equal to qi, which means visually what? They have to be same exact point. Okay. How do I get big stuff happening? Big differences? I need to get something far apart, right? So how do I get the Euclidean distance to grow? Is it better to get a lot of coordinates move a little bit, or is it better to move one coordinate a lot?
Move.
So what I'm asking effectively reflects the difference between the square 2 norm versus one norm or 3 norm. It depends on this exponent here, right? If I have squares or cubes or fourths, the easiest way to make a difference, to create a large difference, is to increase one of the differences a lot. If you know from data science, this root mean square error uses a square, and in root mean square error, you get a higher difference when something is significantly different than you get few small differences. This has to do also with L2 regularization in machine learning. It doesn't let you have very high coefficients because of these reasons. It prefers to have small differences, but many of them. Because the square, imagine if I have an overall difference of say 3, I could have a difference of 3 split into 3 coordinates, 1, 1, 1. Then I get 1 square plus 1 square plus 1 square. Or I can have the whole 3 on 1 dimension. In this case, I get 9. Okay? What's happening with the dot product? Same analysis. When things happen to be 0, or maybe not 0. Is there a minimum or maximum here?
No.
What's the minimum or maximum? Or how do I get low values and how do I get big values?
The angle between the matters, between the two vectors.
The what?
Angle.
Yeah, the angle is going to matter in cosine, which is very similar to the dot product, but we need to do something.
Normalize.
Right, we need to normalize the dot product to get the angle checking in. But before we do that, how does this act? How do you get small values or big values in the dot products?
Same,
When they're similar.
the value of the vector is high.
Hmm?
The value of the vector is high.
So, of course, if the reason for normalization is that if some d, for example, this d, gets very close to 0, then all coordinates are 0. And if all coordinates are 0, it doesn't matter q, I'm going to get a 0 in here because everything is going to multiply with a 0. Right? So in order to analyze the product, we have to set some sort of length or ball where we're looking at. Right? So assuming these things cannot go very far out or very far in, assuming they all like on a ball or a circle, how two things are going to have a high, when do I get a high result? Yeah. In other words, let me put it in English. If I say D and Q, both vectors, have to have the same amount of small values and big values because they are on a circle or ball in 3D. And on this circle, to increase one coordinate, you have to decrease other coordinates. You can't increase all coordinates or decrease all coordinates. That means going in or out, but you can't go in and out. Suppose you fix this ball that you are in. So then, what vectors will have high dot product if they are constrained to be on this ball?
When they're equivalent.
When they are?
Equivalent.
When they're the same.
When they're the same, meaning when high coordinates for one correspond to high coordinates for the other. Because if you look at this product, when you have high values multiplying with high values, you get the high product, but when you get high values multiplied with low values, that's where you get overall a small. This is particularly interesting when the values can be negative. Like those vectors are not restricted in general to be in the first quadrant here, which means all positive. Right? The coordinates can be anywhere. So then when do I get a 0? dot product, when do I get a 0?
These one is zero.
When?
One vector is all zero.
Right, but that's not the only case, right?
They're perpendicular.
When they are, remember geometry, 7th grade? When the vectors are perpendicular, we get a 0. And when do I get the smallest possible value, apart from making things in or out? So suppose I'm restricted. How do I get the smallest possible value? Or the highest possible value? Yeah. When they're opposite, I get the smallest. That corresponds to a cosine of, if I normalize, -1. And the highest is when they align the same direction. That corresponds to a cosine of 1. So what is cosine? Let's write cosine down here. Anybody remember the cosine formula? Dot product, right? Norm of D times the norm of Q. The norm being the square root of the. Okay. So as it happens, cosine kind of works for my intent here. I want to measure how similar query is with a document, or actually any two documents, anything that's represented. Why cosine works well? Why that normalization? There's something to do with text that makes that normalization good for me. Suppose I take this query nuclear bomb, right? And I want to match it to a bunch of documents, million documents. If I don't normalize, there's a certain effect of documents that's going to come into play. What is that? Like even though some documents contain the word nuclear and other words do not, out of the ones that, if first of all, if the query is nuclear bomb and I'm looking at documents that do not contain the word nuclear and bomb, I'm going to get a 0, right? So focusing on documents that contain at least one of the words. What characteristic of documents is going to come into play here? Length. Because longer documents, just because they're longer, they're more likely to contain any word, even the word nuclear, right? A document that is half a page is less likely to contain a specific word than a document that is 300 pages. Agreed? So I think this cosine deals with the length, kind of, in a way that I like. Because by normalizing by the length of D here, I'm saying the scoring function accounts in a certain way, maybe not the best way, but accounts somehow for long documents. In fact, geometrically, cosine is a reflection of the angle. Cosine has to do with measurement of this angle. A cosine of 1 corresponds to the angle of 0. Cosine of 0 corresponds to the angle of 90 degrees. And cosine of -1 corresponds to an angle of 180. Now what happens with the document length? Suppose I play this toyish example where I take a document. I have the term document matrix there. I have all the words with counts. Suppose I copy paste the document into itself. What did I do in terms of the counts? I pick this document 2 and I say, okay, take the document and make it twice the document. What happened with all the counts? Doubled. What if I paste it again? Triple. What happened to the vectorial representation when I copy paste the document into itself? As a vector, what happened with D? It goes up, right? Now this is 2D. And if I paste it again? 3D. But my cosine is measuring what? The angle. When I do this 2D, 3D, did I change the angle? No. So the cosine is independent of how many times copy-paste of that document happened. Of course, this is in theory. You know what I tell you about theory when you go home? Yeah. It's a good idea to normalize, Of course, we don't really copy paste the document into itself, so the counts don't all multiply by the same value. But still, it's much better than not doing anything, like using the dot product plain. So this is the idea here, that I'm measuring the angle between the query and the document. And if a document is long, it accounts for these legs by saying it's only the angle matter. To change this angle, I need to change the relative frequency of the words, right? By keeping the same relative frequency of the words, aka doubling or multiplying or 1.5 or something like this, the angle doesn't change, the cosine doesn't change. Okay? There's another thing that's very beneficial with these vector space models. We're going to talk in a moment about representation, which is who's D1, D2, and DD. So far, if I look at that matrix there, who's this? What are those words? Number of occurrences, or TF, each one of them is a word, right? I know exactly which one is word 1, which one is word 2, which one is word D. So that's consistent across everything I'm doing. Word number 3 is Virgil. That's why the coordinate of everybody, every document, coordinate number 3 will be how many times Virgil appears in the document. What happens with the query? Into a query, most queries, we don't expect those counts to be more than 1, do we? I mean, how many queries have the same word twice? Very few, and if they do, it's probably a typo. Some person didn't remember he typed something and typed it again later on, right? It's very unlikely information retrieval to really mean to put a word algorithm or nuclear twice in a query to kind of emphasize that I want the word nuclear twice, right? I mean that's not how it works. So we can assume very easily for homework 1, but also in reality, that the query representation has 1. It doesn't matter, there's no counts here, it's just which words, which keywords are in there. So for query, we care about which one of these cues are 1 or 0, right? 1 or 0. So if that's the case, what happens now with this formula? Let's say approximately equal. So I'm going to rewrite the numerator. I'm going to say this is a sum over the terms that appear in the query, right? For this, or coordinates, because now the terms are coordinates for me. So I'm going to say, look at those words that appear in the query. I'm going to assume all of them have the value 1. And I simply have to sum up those DT scores, right? I look at only the coordinates that are in the query, and I say for those coordinates, you get D, that coordinate, times 1. And for the ones that do not appear, you get D coordinate times 0. So I'm not going to list those. And for the numerator, I'm going to still have the length of D, but I'm going to skip the length of the query. I'm going to say, okay, I'm not going to normalize by the query. Why is that? What? The length of the query geometrically is not 1 or 0. It's still an Euclidean formula with squares in it and whatnot. But remember, I'm computing the scoring ranking functions. The actual score values are not that important. I'm using the scoring function to do what? Rank the documents, right? That's what I'm using it for, to produce a rank list. So every part of the formula that is the same for all documents, like this norm of Q here, it doesn't matter what it is. It's going to multiply or divide all the scores with some value. It's not going to change the ranking. Who's with me? Hands up. Hands up, please. Okay. So I'm skipping this. So now what do I have? I'm saying go over the query terms. How many query terms can I expect? After you guys take manually out those documents, will, present, how many keywords are actually meaningful remaining there? 2 or 3. So I'm going over those particular 3 keywords, and I say sum up the document representation for those 3 keywords. That is, so suppose I'm nuclear and bomb. This is one word, there's the other word. How do I score a document here? According to my latest formula. I sum up this value here with this value here, divide by document length. That's my score. Of course, I still don't want to do this for every single document. I only want to do it for the ones that are not going to give me a crystal 0. Most documents will not contain either one of those. I don't want to sum up 0 plus 0, 0 plus 0, 80,000 times. So I have to get first a list of documents that don't have 0 everywhere. That won't be too many, and then I just have to sum up. So that's a basic introduction into how vector space models work. Now the complications arrive in, not for the homework, but people have thought quite hard about who is DI. So D component I, or DT. The basic version is the TF, right, term frequency, for that document of the word in position T. If that word in position T is the word nuclear, really means count. Count how many times that word appears in that document. So count, frequency, TF, occurrences means the same thing. How many times? Okay? Here's how other people have thought, okay? How about a different version that is TF, like before, times this IDF value. IDF is only for the word, the term. So IDF of a word, what was mentioned before, does not depend on the document. It's a characteristic of that, how rare is that word. So the formula is very easy. Anybody knows this number? IDF of a word is a logarithm of number of documents n divided, I think I get it right, but we can check the notes. This is the number of docs containing that word. I think it's this. So if I mean, it's a heuristic like everything else in here. Like people have tried out different things that worked. So I mean, anybody can come up with some heuristic. The idea here is that if this word appears in all the documents, what is this fraction?
Very high.
1. Because n is the number of documents. So if this is 1, log of 1 is 0. But if this appears only in one document, or very few, then I get a high IDF. Right? So this can be computed in advance for every word. Just check up these DF values. By the way, DF, or document frequency, is that number of docs containing the word, DF of a word. Just one important observation here, this does not count how many times the word appears in a document. So it doesn't matter if it appears once, or twice, or 1,000 times. It only counts how many documents contain that word, independent of the occurrences. The more documents contain it, the less the IDF. The higher the DF value, the smaller the IDF value. It's 1 over. Okay, so I can do that. I can say, okay, this is one version. dt equal to what? Which is the representation of documents? That's what I'm getting at. What do I represent? Other people have thought, I like the IDF idea, but I don't like the TF. The reason for me not liking the TF is that people have thought, I think they're right, that TF is a linear function, right? It increases for every occurrences you see, it increases by 1. Right? If I see the word twice, I get a 2. If I see it 3 times, I get a 3. 4 times, I get a 4. 200 times, I get 200. What people have said is, take a word like China or nuclear. If it appears once, that's a big deal. Like it's a very specific word, it gives you very clear information. If it appears twice, That's still a big deal, perhaps not as big as the first one, because it's already about nuclear. But once it appears like 20 times, doesn't matter the 21 time? Maybe still does, because nuclear it's a huge deal, so even the 21 times matter. How about if it appears only 200 times? If I see it one more time, do I want to increase my score linearly into number of occurrences? So let me show you that picture. What people have thought here is, here's the TF. This is the occurrences, 0 to maximum. Here's the TF function. This is the DT. If I use the TF for every occurrence, I get 1 point. And it just keeps going. Words that happen to be very frequent in a document, they give you really a high score. That's one of the ways people have used adversarially. Remember I said about bad people? How do I increase my score?
Copy paste.
I create at the bottom of my document whatever I write whatever I need, but at the bottom I type some word like 1,000 times or 2,000 times. And then everything that uses the TF will have a gigantic score for this TF if it increases linearly. So people have thought, wait a minute, I want something that increases linearly in the beginning because the first occurrences really matter. But then after a while, it just doesn't matter that you keep increasing. So for 1 unit, later on, 1 unit of increase doesn't actually increase the value that much. Make sense? Diminishing returns. So how do I do that? I want to keep the idea, that's the importance of the words, but I want to say, look, I'm looking at this TF count, and I say, I want to curve this asymptotically down, somehow. So I still want to increase early on, but then, so I think there's a formula there that says something like, use the TF value, the original TF value, plus some coefficient, say, K, I think, over TF plus epsilon K. So this, you should know this in mathematics. It's a very basic phenomenon, simple mechanism to create what's called a smoothing operator. Of course, K and epsilon are parameters here. So if TF is 0, what is this fraction?
K.
K by epsilon K, that's 1 over epsilon. So that's kind of my base state. If I get 0 count, how much do I want that to count? If I really want to count as 0, what do I have to do? Make epsilon very big. And then, how do I control this increasing rate? You see, if TF goes to infinity, where is this fraction going to go? 1. I can fix it not go to 1 by adding another coefficient to go to 3 or to 5 to whatever I want. What controls this roundness? How much does it go like straight and then one starts rounding? So K, I think, controls that, right? At what point in here I get, say, a certain value? If I put K equal 100, say I put K equal 1,000 here. I still start with 1 over epsilon. But then when I add TF equal 1, what do I get? 1 plus 1,000 divided by 1 plus 1,000 epsilon. That's still effectively 1 over epsilon. So that means a value of 1 did not actually increase that much. Right? So for a large K, I get flat from the beginning, but for a small K, I get a different effect. So you can play with this formula, which is very simple algebraically, like you can see, and you can kind of plot it to see what kind of curves you get. This has a name in information retrieval. It's unfortunate that it has a name, because the guy who invented thought, oh my God, that's such a big discovery, so put my name on it. Let's just call it, rounding a flat line, what it is. But you're gonna see this a lot in the formula when they talk about, copy TF, and some people call it Robertson TF or Robertson or copy TF. I don't care about those names, but I do care about not having it linear, because linear accounts correctly for first few occurrences of the word, which matter. But then once I get a word that's very frequent, I'm going to keep increasing that score for no good reason. Because in text, once you see a document more than, say, a few times, you don't want to keep increasing the score. That's what this formula does. Okay? So we are here at representation. So I got that. And then, similar with this, you guys are going to have to look at BM25. BM25 is just another big formula that follows this thing. It contains TF and all kinds of normalizations like this. But I want to bring up, what else can I do? Can I use a different representation? So those are words. A totally different question is, what if I want to use bigrams? Bigrams are a tuple of words, like my name is Virgil Pavlu. Say I'm asking now, effectively, is it the same to put a query Virgil Pavlu and ask for, say, one of these coding functions? Is it the same as adding a bigram here? Suppose I add a bigram, that's a feature that is two words, word one, word two together. So first of all, what should be the value? How many times I see that exact thing close together? How many times is the bigram? So then what's the difference between having a bigram, which means I'm counting how many times I see it, versus just counting the two words separately that may be close or not close in text? If I count it separately, I still can count for occurrences of both words kind of cumulatively, depending how I choose to combine it. All those vector space models, they kind of add up. Add up what you get from this word, query word, plus what you get from that word, plus what you get from that word. If you look at all those vector space models, they effectively a sum of what you get per word weighted by the IDF. For a bigram, the difference is I only get a count or some match when the word appear together. So it makes a difference whether I see Virgil Pavlu together versus a document that has Virgil in the beginning and Pavlu at the end. That won't count as a matching bigram because they're too far away in text. Bigrams, by the way, have a way to account for this distance. It doesn't have to be black and white. It could be high when they're close together and low when they're very far away. Okay? Yes?
So just thinking about, I know we're not talking about indexing, but with bigrams, would you always index all of the bigrams in your document, or would you, just thinking from like...
What are my options to index bigrams? I could go over the text, first of all, and only index the bigrams that I find. The problem with bigrams is that they may, or trigrams, they may be too many to just index all possibilities. If I have 100,000 documents, I may only want to index the bigrams or trigrams that I see in my data. Because trigrams can be easily 100 million, but in my data I won't see 100 trillion trigrams because I only have 80,000 documents. Okay, the number of trigrams in text is still limited by the length of the document, right? So I could add them here in the index, or maybe I can compute them on the fly. Suppose I only index unigrams. Unigrams, I mean token or words. I'm going to need something here in the index to be able to match bigrams. That is,
Positions.
if I have positions, I probably can tell if two words are together or not, right? But if I don't have positions, there's no way to tell. Although, if I only stick to unigrams and positions, I'll have to create a much more fancy mechanism now to match a bigram. I have to get the posting of, or the list of one word, the list of another word, but then I just can add them up. I have to check if there are some positions at least are close, or how many positions are close to each other that will give me a bigram match. My point is that there are many interesting features that I can get for a document PageRank is one of them, right? So I have here the unigrams, maybe I add bigrams. I can add the PageRank if I have web documents, right? I can say, okay, I want to add PageRank. What else can I add in a document that are not simply unigrams or bigrams? Who wrote it? That's an author. If you are on the web, you care if that's from CNN or it's a random blog, right? I'm not a fan of CNN, I'm just saying that most people will trust CNN more than a random document. What else can I add for a document that might be useful? Length of the document, although that can be computed by just summing up the count, but it may be useful to cache it out, put it there, right? What else?
How many links it has?
How many links and outlinks? What else? The latest revision date, how fresh it is. Is it a recent modified document or is it an old thing that stayed like that for 10 years? What else?
Category. Category.
Like?
Like if it's related to education or it is related to technology.
Right. That kind of category might be easier to obtain from content. But categories like where the document originated, you know, is it a blog, or is it a Facebook post, or is it that? That may be useful to have, right? So I know exactly what kind of document it is. What else? You'd be surprised how many features Microsoft has for their documents in the index that are not based on words. Was the document clicked recently? Was the document containing people's names in it or not? Is this document written in proper English or not? And if it's not, does it have Indian mistakes or Chinese kind of mistakes? Because it turns out, based on the language, the native language of people, people make certain kind of mistakes when they write. Is it a document that has a certain formatting, header, you know, content, like a Wikipedia document, or is it a plain text, or is it kind of an advertisement document? How many pictures are in the document? All kinds of things that people collect. Microsoft has about 1,800 features that are not words. And then to make use of those features, they use a machine learning algorithm to use all of them in the end to rank them. So they use a machine learning for this coding function, but based not just on words. There's initial filtering of content when you put a query into Bing that says, okay, just restrict to documents that seem to have those words or similar words to the ones you're looking for, to not have to deal with all the candidates that you don't need. But then there's a machine learning that takes into account many, many features, including features that are not about the document, like your IP and what queries you put before. All systems do that. So in practice, words feature more like a filter. I want to only restrict to documents that are interesting content-wise. But then commercial system, which is not what we're going to do, they have a machine learning algorithm that rank a lot of features for these documents. So beyond basic information retrieval, there's a lot more columns here that have to play out. And this information retrieval was done before Google. Alta Vista were kind of like that, matching words and produce the list that they have. I'm not sure all of you know about Alta Vista, but something when Google came on. Recently, we have much more stuff. Here are our TAs. We'll take a break now. 3 TAs. One of them is on the way, flying over the Pacific, I think. So we'll take a break, and then these guys will show you a little bit of Elasticsearch after the break. Okay? We got as far as vector models. We had enough to do the homework. I did talk about the homework, but not about the Elasticsearch. So you're going to be my example with you Mac? Well, programming is a big deal in this class, especially double speed. If you, I should say that, I hope it was clear, but if you have struggled with programming in general, it'd be impossible to take this class double speed. But if you don't know Python, but you're very good at Java, that's fine. Or Perl. Actually, Perl can do this very, very easily because Perl with text works very well. So we're gonna let you choose your programming language more or less, except for some languages that we think are very difficult. But if you have difficulty programming in general, like me, like I'm not a good programmer, I would have a hard time taking this class. I'm just kidding. No, I'm serious about the programming part. If you have troubles with understanding mathematically, you know, okay, I'm not sure what the formula is, I'm not sure how to use Elasticsearch, I'm not sure how to evaluate things, that's easy. But if you struggle with programming in general, not at all recommended to take this class double speed. So if your issue is that you can do Java, then do Java, that's fine. Many people have done Java and succeeded. I think it's harder if you don't know any language to choose Java or Python. I think Python definitely worth the effort of learning more Python, and it'd be easier here. But the TAs won't grade your language. Only half an hour on the camera. That's okay. Right. So let's introduce ourselves. I'm Virgil, you already know that.
My name is Akshat. I'm Kevin. I'm Kevin.
So we have another TA, Prasad, but as I said, he's flying over the ocean right now. There are 4 TAs. And typically, we let the TAs organize the office hours. I don't step over them unless there is a big problem. Hopefully we won't have any such problems. In the past, we did it as a first come, first serve basis as office hours. But if you have a certain preference between them, especially if you already talk about, say, homework 2 with one of them, and you have to fix something and come back, it'd be a lot easier to come back to the same TA rather than explaining from the beginning what you've done to another TA. Right? They might also choose to split certain parts of the assignments between them, like indexing, certain parts of the indexing aspect. How do you write your files and stuff like that? Would be one of them. Other one to check because the problems may have parts of the homeworks, so they might decide I'm going to deal with all these parts and you're going to deal with all that part. That's up to them. So they will decide those things. We'll have a rubric, or even easier, they'll have for each homework some minimum requirements. For homework 1, those performance numbers will be posted. How much do I need for those systems to count as good? They also have a set of standard questions to ask. Like for this one, they will ask, okay, show me where your language model is, how you do smoothing, or how you represent the documents, or how do you implement the cosine formula, things like that. So now they'll show you a little bit of Elasticsearch.
Hi. So first, I think we should download Elasticsearch 5.4.3, which we are currently using for our testing. And for the assignment, you might choose the current version, but for the demo purposes, we are using 5.4.3 here. So for Mac, I think you can use this curl command to download 5.4.3, and you can unzip the file and go to that directly, and to run the Elasticsearch, you have to just use this command to get it running. It will run on port 9200, and similarly there is a tool called Kibana where you can visualize all the documents which you have indexed in the Elasticsearch. So it's basically a UI, bootstrap UI, which you can view all the documents, all the statistics, and run simple command for getting the metadata and statistics of the indices. So yeah, I have Elasticsearch running here, so I'll just start Elasticsearch.
Can you make this bigger? The text. you can just say Apple Plus. So Elasticsearch adds like a background server that works on port 9200, and everything goes through that port, including the Kibana that listens to it. Now Kibana is another background server that it offers a visual. You don't have to use Kibana, but it's extremely useful in trying things out. Of course, you have to do this from Python or from whatever language you use, but Kibana, I think we're gonna show it next. It's very useful at checking those indexes.
Yeah, similarly, I'll start Kibana too. It starts like /bin Kibana. We'll start on port 5601. So, yeah, when you first load an Elasticsearch at localhost 9200, you just get this JSON format.
Can you make
like
this
it's
bigger?
Yeah.
In the Apple Plus. All right.
So, and like you'll be making indexes, you'll name the index like AP_dataset or something for assignment 1. So to get the details of the index, you will just slash and like type any index. I have corpus here, so I'll get the details of the index, whatever things are there.
Now
So
there's a lot of things here
Yeah.
that we're not gonna need for homework 1, like shards, replicas, all kind of security properties. This is a commercial system, which is free to download. They only pay for maintenance and tutorials, but you can use Elasticsearch for any purpose. And we're not gonna care about all this stuff right now, where to store things, how many shards you have, how to connect to other computers. Eventually we'll learn more features about Elasticsearch. For right now, we need to know how to index basic text documents and how to retrieve those TF counts out.
Similarly, I have Kibana here. So this is just a UI tool. You can go and see all the documents which are indexed here. So I'll just start up with a new index. Like you can go to Dev Tools where you can see commands like simple get and put. Elasticsearch is based on a REST API like format. So like this is the command to get all the indices I have in my Elasticsearch here. So as you can see, I have one named corpus, one named AP dataset, one named .kibana, which is default. So I'll just delete the corpus, which we just saw. So I'll just run this command, and I get an acknowledgement. Now I'll just this is the command which you'll be using to set up a simple index. These are the settings and the analyzer. You'll find these things in the documentation as well. So we have an index set here. When I search for the stats of the index, I'll see it has no documents in it and no mappings as well. Mappings, you'll have to create the type of the documents. You'll have to name the type of the documents which will be inside the index. Here the type is document, so I'll put in the settings document. These are the properties. It will have 3 fields: doc number, text of the document, as well as the document length. And now when I see the mappings, I'll see all the settings for the mappings here. And that's it for the index part. This is all pretty easy when you look at the documentation of Elasticsearch. You can like experiment with all the settings and look for each and every, like through trial and error. You can look for creating an index, setting up all the settings, and like all the setting up all the properties and fields for the index. I'll go like I'm using Python for my demo. So yeah, here I have my Python code. So I have a text file which has a query powerful. So here I'll just create an instance for Elasticsearch. I'll read the file from my path, and this will index 73 documents. So right now we had 0 documents in our corpus index. So using this file, I'll fill up all the using this file, I'll fill up the document number, the text, as well as document length, and tell Elasticsearch to index this document and these documents for me. So yeah, as you can see, this it's just indexing 73 documents, so it didn't take too long. And when I see the stats again, I'll see the count has 73 documents. And you can see all the documents which have been indexed. Like when I click on discover, I can see 73 hits and all the documents with their text in my index. This is my index basically. And yeah, then I'll be like, to get all the statistics about all the words, searching for a query, I'll need the term frequencies and the document frequencies for each and every document which are indexed right now. So for that, I have a small piece of code here which takes a query text which contains the word powerful for now, and I read it line by line, and for every word I search my index where I use a Groovy script, and I take the term frequency for that word in the index, and I'll get the document frequency as well from the result. Document frequency is a number of documents which contain that word, and the term frequency is how many times that word occurs in that document. And when I loop it over and print the result, so I'll get that the word powerful is contained in 2 documents. Here's a document ID with their term frequency, it occurs 2 times, and this is the second document in which powerful occurs, and it occurs 1 time. And you can check it when you search for the word powerful here, just like a Google query, and it will give exactly the 2 documents which I have, and with the word also in that 2 hits. When I add text, I can see document length. So, and even I can use these Kibana commands to search for the same word powerful. So when I search for it, I'll get 2 hits again. I'll get what document ID contains the word powerful, as well as the second document ID which contains it. So all these commands we'll be putting out in Piazza, setting up a basic index, querying it through Kibana. Ultimately, you'll have to do it via code. So we'll be sharing some code snippets too to get you started with.
So to be clear, Kibana is not required. It's just a very useful tool to have to check up things about your index, query, add searches, dig up into data, things like that. But the homework asks you to do this from programming language like Python. Put back the Python thing.
Yeah.
So we're not going to share the Python code, but if you ask them to show you the code, they will do it on their screen at office hours. The rule for code in general for everybody is you can watch his code on his laptop. If you have a question, he says, here's how I'm doing it. That's okay with me to see like somebody else doing what you want to do. What's not okay is to share code electronically. Like here's I wrote this function, I'm sending it to you by email. That's not okay. If you copy paste things from the internet, you have to tell us. We're not picky about the grades, so you're gonna get the grade points. If you're worried about I copied this piece of the internet, you can still get 100% of the homeworks, but you have to tell us that you copied, and you have to prove to us that you understand what that piece does. The worst thing can happen, you take a piece from somewhere, from the internet or from other students or from whatever, and you run it and you don't know what happens. And it does something, maybe the right thing, but the PAs will ask you, okay, why are you doing this here, and you don't know. So that's considered cheating. If you present to us a homework solution code that's not yours and you don't know what it does, that would be considered cheating. But if you say, okay, I got this piece from somewhere, it does the right thing, but I don't understand it yet. Give me another day to understand it. That's okay, okay? Because that's what happens a lot in reality, yes.
So in general, in terms of how the homework's structured, do you have any tests? Like, do you guys have any recommendations for writing tests, or is it kind of just run it and see if it works?
Yeah, for testing purpose, I think you can, for statistics, when you index a file, we'll be putting out a Piazza post where you can check whether your index might be correct. Like, you'll be indexing a lot of documents, so we know the correct number. Like, it doesn't have to be the exact number, like for 85,000 or something, but should be close by. So you'll know the answer.
That's for you to figure out if you've done it okay, but I think you're asking, once you have the homework, how are we gonna evaluate that it works or not?
I was talking about for my own use, to just make sure I'm not messing up, because I do that sometimes.
Yeah, everybody.
Yeah.
So for internally, I think it's, well, again, this is very fast, so you're not gonna have a lot of time to sleep on it, try things out and see what works. You're gonna have to come to office hours, because that thing's gonna speed up a lot. But for the other question, which is, let me get back to this, but the other question which is, I have my homework. Are we gonna write test cases, like people test their software programs and that? Probably not. But they might have certain queries that they have prepared in advance. Say, I'm gonna query your index for the specific word, because I know the answer to that. I know which documents I did, how many counts it has. If I run it on your index and I get a different answer, then something went off. Also, we're gonna know those numbers, these AP values that I showed you. If you produce, those are minimum values. People have produced up to double those values if they work harder on this homework 1 and 2. So they're gonna check that to see if your retrieval system works. Now, in terms for you, what he was answering is, okay, I did the indexing part. How do I know I got it right? Check the number of documents. It's hard to get it wrong with Elasticsearch, the indexing, because once you give it a bunch of documents, it's gonna do its thing. One thing that we didn't talk about today, and we have to address perhaps a little bit on Monday, but then the week after that, is we talk about stop words. You gotta be careful those stop words, that what you index and what you query have to be consistent. In other words, you don't want to query for a stop word that has been removed because Elasticsearch removed those stop words. You're going to get 0 count back, right? So the other issue that we didn't mention at all is the issue of stemming. That is truncating words to their stem root in English language. So like friendship and friend and friendness might all be stemmed to the same word. That's something you have to play with, because if the index is stemmed, you have to stem the queries too, otherwise there will be a mismatch in there. Not a big deal, but you have to make sure you have this consistency. So it's easy to do those searches that they put up, because the search in Kibana looks like this. Put back the Python one. The Python one, this piece of code is easy to figure out. But that's not what the homework is asking you to do. This is all for your internal debugging to make sure you have it right. The homework asks you to obtain the TF and DF values in an efficient way, and then implement the scoring function yourself. I don't know if they have any code for this. For implementing Okapi TF? No. Probably not yet.
No, not yet.
So your job is not to create a Python script that simply asks Elasticsearch to query the index. You can only get the TF and DF values and some other values that you need from the index, statistics, how they call it. But you have to write your own code for Okapi TF. Do you have the homework?
Yeah.
Okay, so if you go down, you have to implement a piece of code that once you obtain the TF values, creates a scoring function, ranks the documents with that function. So the TS will ask you for, there'll be 2 parts. The first part, say infrastructure. Did you set up your index? Did you index the documents? Do you get the right indexing and TF counts back? And once you do that, second part is show me your TF or Okapi TF or the language models part, how that code runs. Does that answer your question? Some people manage to do demo live. Like a lot of this, if it's done efficiently, you can run it within minutes at office hours. but we're not grading efficiency. So if it took 3-4 hours to run your system, then you cannot run it live. You'll have to show some results. Questions? I think that's what they have for today for Elasticsearch. Any questions on how to set this up? I want to make a comment that I make on all my classes, especially programming one. If you use Windows primarily,
For Windows, I think you can just download the zip file and extract it and then just run elasticsearch.batch, the batch file, and it just runs on.
right, Elasticsearch doesn't require any installation. You may have to install some Python packages to deal with it. But my comment is this, if you use Windows primarily, that's a very bad decision. So I think Windows is great for some things, but for computer science, work in academia, it's a terrible choice. And the faster you ditch it, the happier you're going to be. Not to mention that even if you like to work in Windows, the ability to learn Unix, to know how to interact with the Unix-based system, whether it's Linux or any flavor of Mac, it's based on Unix system, having the ability to run the command line or the file systems that way, it's a huge plus later on. So I'd say, we're not going to, again, grade whether you use Windows or not, of course, that's up to you. But it'd be much faster to do certain things on a Unix-based system, not in this class, in general, in academia. Okay. Do we have any questions? Everybody's happy? So again, before we go today, I want to emphasize one more thing. Be very careful about timing. This class, it's overwhelming, even at the regular speed. Not because it's hard, but because people feel it's so easy, and then they discover it's not. At the double speed, this is going to be your primary problem. The primary problem is going to be, and not just that, it's July and August, right? When the temptation is at all corners to go out, to go to the beach, to travel back home, to date the girl, you know, all of that for a boy. You know, it's all in there, and the easiest thing to say or do is to say, why not postpone the homework for tomorrow or for Saturday, right? And then it just becomes impossible. Just be careful with that. The first office hours will be on Thursday. We say just to give you 2 days to play with this stuff. In this class, if you know what you're doing, aka if you are a TA who took the class before, writing the assignments and done it, it's absolutely possible to do it in half of the time the homework is posted. This is 9 days. If you know what you're doing, you can easily do all this in 4 days. But figuring out how stuff works and what you need to do and try the things that don't work first, that's going to take a lot of time. So I'll see you on Thursdays. I'll be at office hours all Thursdays and sometimes Tuesdays or so. One more thing. Monday, Wednesday, we have a class. So the office hours are in the morning. Tuesday, Thursday, Friday, office hours are at 6 p.m., just like the class. But we need to adjust this schedule depending on what constraints we have. So if a lot of people can't make it Thursday night for some reason, we'll change the office hours for Saturday or whatever works. So how many people took a different class, take a different class this term? Only one. That's good, because a different class would be in the way. So are we okay with the schedule? Office hours at night when we have no class, and office hours in the morning when we have a class.